We'll do an example of an integral of a function of two variables. We have the height of some object is given by this function of points x and y in the xy plane. And the function is just, the height is given times x times y. And the region where the object exists is the region where 0 is less than or equal to x is less than or equal to 1, and x is less than or equal to y is less than or equal to 2. To actually find the volume of this object, we will need to set up an integral and then integrate. When setting up the integral, I find it convenient to make a diagram of the region of integration. So xy axes, we have a line x equals 0, we have a line x equals 1, x equals 0, x equals 1. We have a line x less than or equal to y, so the line x equals y. And then the final bound is y equals 2, which is up here somewhere, y equals 2. And as we look at this region, it seems like we'll want to know this point. It seems like these are the four corners of our region, and then the region itself is this zone in here. So we want to set up an integral over this region, and then we want to actually integrate. The volume will be equal to the integral over the region of the height function times little chunks of area. And we need to pick an order of integration in order to set up the integral, in order to replace this part with an iterated integral. There are two possible directions of integration for this problem. We could integrate interior in x, so we would integrate across at all these spots in x, and then we would sum up over all the places where we got a number. Or we could integrate in y first, and sum over all the locations on the x-axis where we produce a number. Integrating with x first, we certainly, everywhere we would be starting at x equals 0, but some places we seem to need to end at this line, while other places we need to end at x equals 1. And so we would need two integrals to write this with x on the interior. However, if we start with y and move vertically, then at every point we can describe this lower bound with this line and this upper bound with this line. So let's use vertical strips to set up this integral. So we'll have an integral, xy, dy, dx. And our upper bound is y equals 2 for everyone. So that's nice to write in, y equals 2. And our lower bound seems to be y equals x. And then our other bounds, we're doing all of this stuff between 0 and 1, so they are x equals 0 and x equals 1. Rewriting, our integral is from 0 to 1 in x, from x to 2 in y, x, y, dy, dx. Now it's time to integrate. When we integrate, we do the interior integral first, and then we'll do the outer integral. This interior integral is in terms of y, so this y is our variable of integration, while this x is just a constant. It could be like a 7, but instead it happens to be an x. So we're just thinking about the integral of y dy, and there's a constant in front of it, and so that's going to be 1/2 y squared, still times that constant. So we get, okay, that outer integral isn't changing, but that inner integral, we've just done it, and we got 1/2 y squared x, that constant, from y equals x to y equals 2. And to complete the integration process, we plug these in. So we're going to get, we have the integral from 0 to 1 dx. I can pull this 1/2 all the way out because it's just completely constant. We still have that x. And then plugging in the first y squared is a 4, and then minus, so 2 squared minus x squared. So 4 minus x squared. And this came from here, and this came from here. Okay, and so now our volume, wrong color, is equal to 1/2 the integral from 0 to 1 of x times 4 minus x squared dx. This is a single variable calculus problem, and we can just find that integral. We'll do that in a moment. To integrate, I will multiply through 1/2 0 to 1 for x minus x cubed dx, so 1/2, and that integral of 4x is 2x squared minus 1/4 x to the 4th from x equals 0 to x equals 1. Plugging in we get 1/2. If we plug in the upper, we're getting numbers. If we plug in the lower, we get 0 and zeros, so we can ignore that bound. And we have 2 minus 1/4, which is equal to 1 minus 1/8, which is equal to 7/8. We were expecting a positive number for this problem, and we got one, so that seems pretty good. Hopefully this is right.